more on this idea of complex conjugates and playing with their properties. So the modulus of z would be the same as the modulus of its conjugate. Because remember, the only difference between the two is the sign of the imaginary part. So the actual size or distance to the origin would be the same. And we saw this in the Argand diagram. The conjugate is a reflection in the x-axis. So that means their arguments will be opposite in sign. One will have a positive angle, the other will have a negative angle. But the actual angle would be the same size. And there's good old ZZ conjugate, which before I was saying, oh, that's the sum of two squares. But now we can just say, oh, it's the modulus squared. A lot easier to say that. And we talked about this before. Remember, you can do it in any order. You can add them together first, then find the conjugate, or find the conjugates, then add them. Same with multiplication, same with division. And the reciprocal, now I can write that a little bit neater. That's the conjugate over the modulus squared. Conjugate over the modulus squared. Okay. Here's an interesting question. So x plus iy is the square root of 6 plus 2i on 3 minus I. Show that x squared plus y squared is equal to 2. Okay. So x plus iy, that's what they've told me it is. So I'm going to play with the conjugates to get this. Well, first of all, I've squared both sides to get rid of the square root sign. But if I play with the conjugate, if that's what x plus iy squared is, well, the conjugate of both sides must also be equal. So I can say the conjugate of x plus iy squared would be the same as the conjugate of 6 plus 2i on 3 minus I. But then, of course, division, the conjugate of that fraction, I could find the conjugate of the numerator over the conjugate of the denominator. So on the left-hand side, the x plus iy could become x minus iy. It's the conjugate. And on the right hand side we now have 6 minus 2i on 3 plus I. So if I combine these two ideas together by multiplication, I end up with a whole heap of difference of two squares. And so on the left hand side I'll get x squared plus y squared squared, and on the right hand side we'll get the sum of two squares, so 36 plus 4, and on the bottom 9 plus 4. So we know x squared plus y squared squared is 4. So therefore, x squared plus y squared is 2. And in this case, it has to be positive 2, because remember, x and y are both real numbers. So when we square them, we know we have to end up with a positive. It's not possible for that to be a negative. Okay, so that's a very quick one. I was just playing with the idea. Our Cambridge doesn't really have an exercise on this, but there's a nice little exercise in Patel 4H.